Okay. So what I have here is just the first page of this error budget spreadsheet. And I want to just talk about the general construction of it. And then later on you can go to the special topic of just me talking about the spreadsheet, but you won't see me because it'll be me using one of those programs that records my voice over while I'm pointing and clicking and dynamically changing the spreadsheet. The first thing in all these spreadsheets is make sure you read at the top how the thing works. For example, here I'm using the units of millimeters. So I'm entering everything in millimeters. You know, the units of the errors are millimeters, not microns, not kilometers. And the results that will show up in the end for this particular machine, it's an 8-axis machine. And the vector in the end is the vector error between the tooltip and the workpiece where I want to be on it. Assuming I really wanted to be here, it's telling me that the magnitude of the error is, the systematic error is 0.165 millimeters, and the magnitude of the expected random error is 0.136 millimeters. Okay? There's a lot of other information contained in it, such as what it's expecting the pitch, yaw, roll error to be, as well as the 3 translational errors. The spreadsheet allows you to enter in coordinate axes up to 15. You can turn different errors on and off. You can turn off or on systematic errors just by typing in on or off. Thermal errors or dynamic errors. These two elements here, you're going to have to write your own bits of code based on, for example, the length of the structural loop between 2 axes, the type of material, and the expected temperature difference to come up with an expansion between 2 axes in the machine. The random errors are always entered in based on the type of logic we talked before about, for example, these moving carriages. Now, you're not limited to moving carriages of these modular types. You could also do a similar rationale of estimating the types of pitch, yaw, roll errors if you had sliding contact bearings, again, based on the spacing between the bearing pads and the types of tolerances you would incur for each of the bearing pads. So the name of the game here is to have an idea of the structural loop of the machine passing through the centers of stiffness of each of the major axes. And they don't have to always be the moving axes. It could be this axis is bolted to that axis. Well, there is no random error, but there is now a systematic error that's in there from the way it was manufactured. Some of this will be experience. Some of this will be rational, deterministic. Here is the math behind it. And note that the key is going to be, with time, the more you do this when you're designing a machine, and then after you've designed the machine and you've built the machine and the machine is measured, you go back and say, that worked really nice. That was excellent. Yeah, I got that one right. Equally valuable is, it didn't work anywhere the way I thought it was. It was twice as good. Excellent. And the other one won't even bother to do the crying scene. Your job as an engineer is to get better, better, and better, and that's where practice, practice, practice. But the practice you want to do is based on rational, deterministic thought. And when you make some sort of assumption for how some bearings or structures interacted based on the industry you're in, you will gain experience about how to model the types of machines that you're designing. And you'll get better and better at it, and you'll customize your own spreadsheet, or if you want to write it in MATLAB or whatever code you want to use, that's fine. But the fundamental theory stays the same. Hence, this is what precision machine design is all about. It's all about the fundamentals of design, learning what each piece can do, and then how do all the pieces come together to form an entire machine. So good luck with your machine designs. May the microns be with you.